Okay, logarithms. So let's first talk about. So this is 7.1, by the way. I didn't put that up there. Let's talk about how this relates to exponential functions, because that's really what they are. Okay, so a little bit of review here. Let's say that we were going to graph something like y is equal to 2 to the power of x. Okay, so what does that look like again? So what was that all about? Let's actually just graph that quick and remind ourselves. So y is equal to 2 to the power of x. And there you go, right? Oh, put that down. We get that telltale exponential graph, right? Where it's crossing at the point 0, 1, right? As a little review here, remember what would happen if I had like a number out front? So if it would have been something like, 3 times 2 to the power of x. Do you remember how that makes it cross now at 3? Like that's going to be my y-intercept. Okay, so that was the case. So now what we're going to be doing is we're going to start talking about the reciprocal function of this. Okay, so I know reciprocal is a big word, but what that means is that all of my x values here, right? So if I look at this one, right? So if I put in the point, so 2 to the power of, let's say 1, right? So when x is 1, right? So if I put like an x in, or like a 1 in for x there, then y would be 2. So that would be that point right, if we can stop it there, right there, right? 1, 2. And then if I made x equal to 2, right? So if I threw a 2 in for x there, then that's going to be 2 to the power of 2, which is 4. So then that brings me up to here, right? So now I'm going to, when x is 2, y is 4. Okay, so what reciprocal means is that if I actually take this, oh, doesn't like that. If I take this, the x value there of 2 and the y value of 4, it means I'm actually going to like flip those things around, right? So the point on the reciprocal of this would be 4, 2, right? And down here where this was 1, 2, the reciprocal graph would be 2, 1, right? So what I'm talking about, what the way this would look is it would be this. It would be x is equal to 2 to the power of y. Okay, so sorry, I got a little distracted there. So can't remember where I was at, but if I rewrite this exponential function, y is equal to 2 to the power of x, right? The reciprocal of that would be x is equal to 2 to the power of y. Just like flipping those two things around, right? So all my x's are y, or all my x's are y's, and my y's are x's, okay, essentially, right? Now, if I look at this graph, right, what that would be, like I said, is that like this point here that I had 1, 2. Well, it would actually be at the point 2, 1. So this graph should actually have that as being a point like right there, right? And then the next one would be at, well, normally the graph is at 2, 4. So it should actually be at 4, 2. So it would be over 4 on the x-axis and then up 2. So that'd be the next point there, right? And I'll show you what that looks like in a second when I actually graph it. But that's the idea with a reciprocal function. But so now the problem here is that we don't typically write functions as x is equal to something y, right? We want it to be like y is equal to something x. So we have to actually write this in a different way, and that's where logs come in. So this right here could actually be written in this form. It'd be the same as y is equal to log and then base 2 of x. So this thing right there is the same thing as that right there. They're saying the exact same thing. This one could go in your calculator better. Like you could actually graph this one, and I'll do that for right now. So let's see what that looks like. So that would be, I'm going to graph it below this one. So that'd be y is equal to log, and now I could write log. Yeah, actually I do have to write log base 2. I hope I can do base on this. Base 2, yep, of x. And what do we get? All right. So that's what I was talking about there, right? Is that, can you see now that we had, so 1, 2 on the original, is now I should have the point 2 comma 1, and there it is right there, right? 2 comma 1 on the other one. So that point is like reflected. And what's it reflected around? Well, watch this. I'm going to draw one more line. I'm going to draw the line y is equal to x. And you can kind of see here now that we've got this purple line is being just reflected around the line y is equal to x, right? Line y is equal to x is just like a perfect diagonal, right? Going up. And that's really what the logarithmic graph is. It's a reflection over that line, essentially. Okay, so that's the idea. Good news for you guys. I made this one as y is equal to 2 to the power of x and then went log base 2. For math 30-2, we actually don't need to do, like when we're graphing anyway, we're not going to have any like base 2 or base 3 or anything else. All we're ever going to do is we're going to have it written like this. It'll be y is equal to log, and then it's only ever going to be base 10 of x whenever we're graphing these things. Okay, so we don't have to worry about changing the base out to figure out the way the graphs look. And another way of writing that is this: y is equal to, and then it's just log x. It is base 10. You have to like remember that there is a 10 there, but base 10 gets used so often that in shorthand it's just written like this: y is equal to log x. So if I type that one in, okay, so let's just delete these ones. So this will be just log, I could write base 10 if I wanted to, but it'd be the same thing as just log x, right? So that's the way that one looks, right? And this makes sense because look over here, like when x is 10, y is 1, which what would the opposite of this be? That would be the graph y is equal to 10 to the power of x, right? Now those are being reflected around that line y is equal to x, right? It's like a perfect reflection about that one. Okay, so hopefully that's making a little bit of sense. For the most part, guys, you just need to have like a general understanding of the shape of these graphs. So if some of this is going a little bit over your head, that's okay. We don't need to get like too into the weeds. Just the general shape is good. So before we move on a little bit though, the other thing that we're responsible for. So I said that, you know, we're only going to be doing base 10, but I kind of lied. The other part that we have to know is actually, and it kind of sucks, I got to bring up like a new concept. I'm not going to talk much about it at all, but there is an exponential, like a really, really common number in math. And that's going to be this one where it's y is equal to e to the power of x. Now you haven't seen that symbol e before. It's called Euler's number. And it's just a really common number in math. And what is it? Well, it's actually an irrational number, kind of like pi. You know how pi is 3.14 yada yada yada. I can't even remember what Euler's number is for right now, but it's like 2 point something. Like again, it's gonna be numbers that go on forever. But it's just another one of those like constants in nature that happens so frequently that it's in a lot of our equations that we'll use. So you guys are responsible just for kind of like knowing of it, right? So if I typed in e to the power of, actually there it is right there, right? 2.718 yada yada yada. So e to the power of x, it gives us our same exponential graph, right? But then the other part of this, another one that comes up quite often, it's actually called the natural log. And the natural log is exactly the opposite of this. Okay, so in the same way that 10 to the power of x, right? Y is equal to 10 to the power of x. The opposite of that, or like the reciprocal of that, was y is equal to log, you know, base 10 or just log of x. Those are like, those go together. We've got the same thing here where it's going to be y is equal to e to the power of x. The opposite of that, or the reciprocal of that, is y is equal to, and then it's this symbol. It's the natural log, just ln, without the o in it, right? Or I guess there's no g either, but natural log of x. Okay, so if I type that in, you can see, so the natural log of x, I could have had y up here too, by the way, so y is equal to. Okay, but on the next one, y is equal to, and then ln of x. You can see we get that same thing, right? So hopefully that makes a bit of sense. Let's compare these while we're looking at it though too. So there's e to the power of x and the natural log of x. So those two are like a pair, they go together. But then we can also put on the graph, let's put the other one too. So 10 to the power of x and log of x, right? So those are like the four, right? Those are the four that we need to know. Just notice that the blue line here, right? 10 to the power of x. Well, that rises more sharply than e to the power of x, which makes sense because e was like 2.7, right? This is 10, so it's going to rise quicker. And the log of x is going to, diverge quicker like this than the natural log of x, right? So this is kind of a good little picture to kind of have in mind when you're doing that. But okay, so that's the idea. So now that's pretty much it. There's just one last little twist we have to put on this, and that's if we are gonna reflect it. So here's the other thing. So let's just write the natural log or the log, doesn't matter. I'll do natural log. So we got the natural log of x, right? And I guess that should be y is equal to. So natural log of x, right? I just want you to see now, so you can zoom in or whatever there, that the other type of graph that you might see or that you will see is if you put a negative out front of this thing. So if I went negative natural log of x, do you see what happened there? It flips over the x-axis. So when it was just the natural log of x, it started low in quadrant 4, right? That's this quadrant 4 down here. And then it goes up into quadrant 1, right? It's like rising from left to right there, okay? But if I make it negative, then it starts high in quadrant 1 and then comes down into quadrant 4. And it's like going down a hill there. So that negative flips it. So essentially what happened there, right, is when I went y is equal to, so natural log, remember y, like this is my y, these are all my y values. So let's say if I was like looking at this point right here, right? So let's say like a y value of like 2, wherever that is, right? Well, at that, once I made it negative, right? Once I threw like a negative out front, well, what that did is that took that point that was up here and positive and it moved it down here. Okay. And then the same thing for these ones. This point that was -2, if I go negative times -2, now that's positive. Now that's going to bring it up here. So it just flips. You see how it flips everything over the x-axis? That's all that's happening. So if it was up top, now it's down below. If it was down below, now it's up top. Okay. So that's the last of it, right? So that's all we have to make sure that we understand for our log graphs. So now let's look at a few and just see if we can figure this out, right? So looking at this question, it says which function matches each graph below? Provide your reasoning. Okay, well, first off, first one, exponential, right? We got an exponential function. I'm gonna zoom in a little bit. So we got an exponential function, right? So it's something to the power of x. So what would that look like, right? So here, let's even just type it in. So we don't need to type it in. We can figure this out. When we had an exponential graph in the last lesson, right? Remember how this number is important to tell you like the general shape of the graph? Because this is saying like, 2 to the power of some number. So that'd be like 2 to the power of 1 or 2 to the power of 2, 2 to the power of 3, right? Anything else there. So that graph would be getting bigger and bigger and bigger over time, right? If you started at like 0 and then you'd be like going up and up and up and up, right? Okay, so that was this general shape. And if we can remember, the number out front, that I just said this at the beginning of the video, the number out front there, that is where you cross the y-axis. So this one makes sense, right? Because if x was 0, right, if I put a 0 in there, that'd be 2 to the power of 0 is 1. So then y would be equal to 5. So then I'd be at 5, or 5, a little bit lower, right there. Okay, so that's our first one. So this one would be I. Okay, so let's look at the next one here. 2 times 0.1. Now, back to last unit again, if we ever have it was a b value, right? Remember it was y is equal to a b to the x is what we were doing. If you ever have a b value that's greater than 0, but less than 1, right? Then what that's going to do is that thing's going to go down. You're going to get a graph that's looking like this, right? Where it's going down like that. So I'm looking for that one. And there you go. That's this one over here, right? So this is going to be I. Now the new stuff, we've got 6 times log x. All right, so log x, they start low in quadrant 4 and they end up high in quadrant 1. That's that standard log graph, right? I don't even really need to know like log base, 6 times whatever. None of that really matters. The fact that it's positive out front means it's not flipping. I'm not flipping it upside down like I was just talking about. This is going up. I don't need to know a lot of the rest, right? Just that in general. Okay. Now, y is equal to -2, and then natural log of x, right? Natural log of x is like really the same thing as log of x. It's going to have the same general shape. But what's key here is this negative. So the negative is going to give me the general shape of this graph, and that should be this guy, right? Where it's starting from like high in this quadrant and working its way down that way. Okay. So that's it. That's the idea for this lesson. So just key ideas here are log graphs, natural log or log base 10. They're always going to have an x-intercept, and they're always going to have one x-intercept, right? Because they're always going to cross either like this or like this. And actually, for our purposes, everything we do in 30-2, it's always going to cross right at 1 every time. Okay. Number of y-intercepts, none, right? This thing, it actually approaches y. It never gets to y. So it never actually touches that y-axis on either one. The end behavior is you get a curve that extends from either quadrant 4 to quadrant 1 or quadrant 1 to quadrant 4. So just make sure you understand when to use this one and when to use this one, okay? So this is positive log x. This would be negative log x. Our domain, okay, so domain is what x is allowed to be. This is just saying x always has to be greater than 0. And then range, our range can be anything. It starts infinitely far down and it would go infinitely far up, okay? Okay, and that's the gist of it. So you guys just have a few questions on this one, and I'll see you guys in the next one.